Hello everyone, welcome to my videos on elementary differential equations. This is video number 17 for chapter 3. This will be the last video on the topic of finding a particular solution to a non-homogeneous linear problem, in particular the form of a particular solution. So let's summarize the general approach. So if you have a source term g and it's in a certain form, and we have discussed many cases already, so here we'll be looking at more complicated cases, and the general guideline is the following, and all the cases are actually can be treated in this similar way. So you have a source term g. And the first step, I look at the form of g and I guess the particular solution to be the same form. And first we check if this works or if this can be a problem. So when would this be a problem? Well, that is the case when the form of this g will provide a solution to the homogeneous equation. Then it will never work. And if this is not a solution of the homogeneous equation, then this form will work, and we will use this form as a particular solution. And then if it is a solution to the homogeneous equation, then this doesn't work, then we can take the form and multiply it by t, and sometimes by t squared, if by t doesn't work. Okay, so now we will just summarize various cases without providing examples or testing to see if our claim works. And you can work out examples of this. Okay, so here is summary number 5. Here we consider the case where the source term gt takes the following form, is an exponential function to the power alpha t, and then it can multiply by a cosine beta t plus a sine beta t, a linear combination of them. So here a and b are just two given numbers. Okay, so if g is this, and then at the same time we also compute the two roots, r1 and r2 of the characteristic equation. So we call this R1 and R2. Okay, so here basically we have two cases. Case 1 is the case where the roots are not exactly alpha plus minus I beta. Okay, because if the roots are that, then this form will not work. So if the root is not that, then the form of the particular solution will be taking the same form, that is this exponential function and then a linear combination of sine cosine. So that's exactly the form, and then the linear combination of sine cosine will be with coefficients capital A and capital B, and the capital A and the capital B are the two numbers to be determined for you to find this particular solution. Okay, and then this form would work as long as it is not the solution to the homogeneous problem, meaning where the roots do not match exactly this form. Okay, the second case will be the case where the roots of the characteristic equation exactly matches alpha plus minus I beta. Then we know it doesn't work because this form solves the homogeneous equation for any a and b. So what you do is take that form that doesn't work and multiply by t. Okay, so we have done this trick many times and it always works. Okay, so as I said, we do not provide examples here. We just summarize the result. Okay, so here is another case. We call it summary number 6. So in this case, the g takes the following form. It's some given polynomial times cosine beta t plus another polynomial, possibly different ones, times sine beta t. So the beta here, they're the same. So what's in front of the t is the same number. Okay? And one is sine function, one is cosine function, and they are multiplied by some polynomials of degree n, which are given. Okay, so that's the source term. And now, again, let R1, R2 denote the two roots of the characteristic equation. And then we have two cases. Case 1 is the case where the form of g will already work. Okay, and that is the case where the roots R1, R2 are not equal to plus minus I beta, where beta is the coefficient here. Because you know, if the roots equal to that, then cosine beta t, sine beta t, they are both solutions for the homogeneous equations, and that causes trouble. Okay, so in the case it doesn't cause trouble, then the form of the particular solution will be the same as the form of the source term g. So what is the form of the source term g? Well, it is that a polynomial of degree n times cosine beta t plus another polynomial of degree n times sine beta t. So we will guess the same form. So here we put in a polynomial. We denote the coefficients by an and a all the way down to a naught. Okay, and then plus, so this is multiplied by cosine beta t plus another polynomial times sine beta t. So this is a different polynomial. So we denote the coefficients with b, bn, bn minus 1, all the way to b1 and b0. Okay, so there will be n plus 1 coefficients in A and n plus 1 in B. So totally 2n plus 2 coefficients to be determined. Okay, so that's the case where the form just works. And then there, of course, there's the other case. Okay, so the next case is where this form will not work. That is the roots of the characteristic equation is exactly plus minus I beta. It's the case not included there. Then we know this form will not work because the term A naught cosine beta t and the term B naught sine beta t, they are solutions for the homogeneous equation. Okay, so it won't work. And in this case, we have the standard trick. That is, we take this form that would fail and just multiply it by t. And that new form will always work. Okay, here is summary 7. So here, the source term takes the following form. G of t is a polynomial of degree n times e to the alpha t times, here is a cosine beta t plus b sine beta t, where a and b are just two constants. So the coefficient in front of t is beta for both sine and cosine. Okay, and the Pn is a polynomial of degree n. And again, R1, R2 are the roots of the characteristic equation. Okay, and then we have two cases. The first case were the roots of the characteristic equation R1, R2, and they do not equal to alpha plus minus I beta. Okay, because we know if this is, then the form will not work. Okay, if that is not the case, then the particular solution would take just the same form as the g. So what is the g here? Well, the g here is basically an exponential function. If we multiply the Pn into both, then it's an exponential function times a polynomial times cosine plus another polynomial times sine. Okay, and that's what we will fit in. So capital Y is e to the alpha t, here a polynomial, cosine t, let the polynomial have coefficients a's, a0, a1 to an, and then in front of sine, another polynomial, the coefficient be b0, b1 to bn, and we add them up. So this will be the form of the particular solution. Okay, then in the case where the two roots r1, r2 exactly equals alpha plus minus I beta, then this form doesn't work, because you know the term a naught times cosine beta t and then b naught sine beta t multiplied by e to the at outside will provide a solution for the homogeneous equation. So that will not work. Okay, so what you do will be taking this form here and multiply by a t, as we always do. Okay, so finally, what if there are many terms in the source? So if the source term g, let's say, have several terms, what we can do is we can treat each term separately and find the particular solution for each term, and then add up later. So to be precise, let's say gt equals to g1t plus g2t plus all the way to gnt. There are n terms that are different. Okay, then what one does is that treat each of these g terms separately. Let's say for the gi term on the right hand side, and we will try to find a particular solution. Let's call it capital Yi, and treat it as if the right hand side contains only the gi term. Okay, and do it for all the terms, and then the particular solution y would be adding up all these particular solutions, y1, y2, all the way to yn. Okay, so we claim that adding these yi's up all together will give us a solution, particular solution y, where the right hand side is adding up all these gi terms. So why is this claim true? Well, this claim basically follows from the principle of superposition for linear equations. So we will not go through a proof here. If you are curious, I encourage you to work out a proof by yourself. It's not difficult. Okay, now let's take some example. So we'll go through a couple of them, and in the examples below, we want to just write out the form of a particular solution. We will not work out the details and solve for the coefficients. We were interested in only the form. Okay, so here's an example. So the left hand side is y double prime minus 3y prime minus 4y equal to gt. gt is the right hand side. Now it contains 4 terms: sine 4t, 2 times e to the 4t, e to the 5t, and negative t. Okay, so here it's important to know the form of the solution to the homogeneous equation. That is, we need to find the two roots of the characteristic equation. So characteristic equation will be r squared minus 3r minus 4 equals 0. And you easily find the two roots. r1 is negative 1, r2 is 4. So we know the homogeneous equation will have solution e to the negative t, and the second one is e to the 4t. So when you have e to the 4t to the right hand side, which we eyeball it, we find it, there is this term, then this term needs to be carefully treated. That is, we need to multiply the form by t. Okay, then the form of the particular solution can be done as we suggested. That is, we treat each term separately and then we add them up. Okay, so here I color coded each term. We have red one, blue one, green one, and purple one. So let's take one at a time. So capital YT will be, first we find the solution corresponds to sine 4t. So we know our roots are not plus minus 4i, so this is fine. So we'll fit in the same form. That is a constant times sine plus a constant times cosine 4t. Okay, so this red term here corresponds to this red term. Next, let's look at the blue term, e to the 4t times a constant. And then we see that this is a solution for the homogeneous equation, so we need to multiply it by t. Therefore, we put a constant times t times e to the 4t. Okay, so then next is the green term, e to the 5t. And we know this term is fine because 5 is not R1 or R2. Therefore, we fit in a term of the same type, that is a constant times e to the 5t. And finally, the purple term, negative t. That is a polynomial of degree 1. And then here we see that R1 and R2, none of them is 0. So this form will work. So we'll fit in a polynomial of degree 1, which is a constant times t plus a constant. Okay, there you go. We could almost immediately just write out the form of the particular solution. Our next example is this one. So y double prime plus 16y equal to this g here, which contains 1, 2, 3, 4 terms. Okay, I already pre-color coded it. Okay, so let's for a while neglect the colors there on the g term. Let's look at the characteristic equation and the roots. So we get r squared plus 16, 0, and then we find the roots is plus minus 4i. In this case, we know that the solution for the homogeneous equation is constant times sine 4t plus a constant times cosine 4t. Yeah, therefore we know sine 4t and cosine 4t terms will not work, and they are actually also considered of the same type. Therefore, you see I colored this term and that term in red, although they are not right next to each other. We could rewrite it and put them next to each other. Okay, and then we know the form will not work and we need to multiply it by t. Keep that in mind. Okay, so now we can write out the particular solution. So first consider these red terms, and then we know the form sine function plus cosine function of 4t does not work. We need to multiply by t. Okay, and then there's a constant times sine and the constant times cosine 4t. That's the red term. So this term is corresponding to these two red terms. Okay, now the next one is the blue term. That's cosine t. So this term is fine. So we know for a cosine t, we need to fit in a function containing both sine and cosine in general. Okay, and so we can just fit in a constant times a cosine t plus a constant times sine t. And finally, the sine term is a constant 4, so we will just fit a constant e here. Okay, so that is to fit in each term of its type one by one and add them up, and we are just fitting it in following the summaries we have made. Now let me make a comment for the case corresponding to the blue term, cosine t. So note that in general, if you have a cosine t for a second order equation, in general you fit in both sine and cosine. But here for this example, actually we don't need to fit in sine t. So the reason to fit in both sine and cosine was caused by the term y prime. And here on the left-hand side, we don't have this first derivative term. We have y double prime and y. Therefore, actually, for this problem here, we do not need this guy here. We could actually drop that. But if you put both in as we wrote here with the C and the D, it's still correct, because if you try to fit in this form, you will find that D is 0. Okay, one more example. We want to find the form of y for this equation, y double prime minus 2y prime plus 2y equal to this very long right-hand side. So don't worry about the right-hand side. We will dissect it and look at them one by one. Okay, step 1, to find the roots of the characteristic equation. So we quickly set it up. R squared minus 2r plus 2 is 0. And we find the two roots, and that is 1 plus minus I. Then we know the solution for the homogeneous equation is e to the t times sine t or cosine t. And then we immediately take a look at the right hand side, and we see that this term here, that form will not work. You have to multiply by a t. Okay, so with these informations in hand, we can now tackle each term and write out this form of the particular solution. So first look at the red one. So as the comment here, this one, the form will not work, so we have to multiply it by a t. So for the red one, the corresponding term would be t times et, and then some constant times cosine t plus some constant times sine t. Okay, so that is for the red term. The next term, we put it in blue, is e to the t times sine 2t. So this form is fine. So let's fit in this form. So we'll have et times, so because you always have to fit both sine and cosine. Okay, so a constant cosine 2t plus another constant sine 2t. So that's for the second term. Now let's look further. We see that the third and the fourth term can actually be lumped together. We can think this is t plus 4 times e to the t. So a polynomial of degree 1 times an exponential function e to the negative t. Okay, and that form we can just fit in. So we'll fit in a polynomial of degree 1, so c1t plus c0 times e to the negative t, where the c1 and c0 and c1 are the two coefficients to be determined. And finally, let's look at the last two terms. One is t squared, one is negative 3. And we see that we can lump them together. This is a polynomial of degree 2. And that's what we fit in, a polynomial of degree 2. So the coefficients are d1 for t squared plus d2 for t squared plus d1 for t and plus d0 for the constant term. Okay, so here we have many coefficients, 1, 2, 3, 4, 5, 6, 7, 8, 9 of them to be determined. And we can plug this back in and find them. And we can be rest assured that we can find them because this form is a correct form. Okay, so that's the last example. And I hope that after seeing these examples, you will no longer be afraid of seeing multiple terms on the right-hand side. Simply treat them one by one as if that one stands alone, and just follow all the summaries that you have learned and put in the correct form, and there you go, you can solve it. Okay, so that's all I have to say on the topic of finding particular solutions. Okay, so next video we'll start on a new topic. Okay, so I hope you enjoyed this one, and I'll see you next time.